Hello, welcome once again to our physics class in LFI Educates. We are in this chapter 9, Ray Optics and Optical Instruments. Today we are going to discuss about critical angle. Critical angle is that angle of incidence for which the angle of refraction is 90 degree. When light passes from denser medium to rarer medium, this phenomenon happens when light travels from denser medium to rarer medium. Suppose if I take the interface here XY like this is denser suppose, and this is rarer. Then when light travels from denser medium to rarer medium, this is your angle of incidence. Let me take it as I1. Then light will go or bend away from the normal like this. There you will get the angle of refraction. In this case, angle of refraction is more than the angle of incidence. Now, if I increase the angle of incidence, say as I2, then the angle of refraction again will become more. Suppose think that this way the light is refracting. So here you are having the angle of refraction as 90 degree in the second case. So this angle of incidence in this case for the second ray will be called as critical angle, because the angle of refraction is here exactly 90 degree. So this term I2 will be called as critical angle, and we write it as IC as well. We write it as IC, the critical angle. Now, again I repeat it once more. The angle of incidence for which the angle of refraction is 90 degree, that angle of incidence is called the critical angle. In this case, you have to prove one relation to prove the refractive index, the relative refractive index mu 21, that is denser medium to rarer medium, is equal to the reciprocal of sine of the critical angle. Let us prove and say. To prove this, you don't have to draw two rays. So this first part I am rubbing it. This angle of incidence, the first one, remove it. Then this angle of refraction will be 90 degree, and this angle of incidence will be called as critical angle, IC. So if you use Snell's law, when light is entering from denser medium to rarer medium, sin I by sin R is equal to refractive index of first medium with respect to second. Light is entering from denser to rarer. Then it will look like this. When I, the angle of incidence will become equal to the critical angle, then the angle of refraction is 90 degree. So if you put these two values here, sin I will write the sin IC, and then sin R, that is 90 degree, sin 90 degree is equal to refractive index of first medium with respect to second. And sin 90, you all know that it is equal to 1. So it will be sin IC is equal to refractive index of first medium with respect to second, or rarer to denser. Now if I reciprocate it, then it will look like this: 1 by refractive index of second medium with respect to first, that is equal to sin IC. So if I cross multiply now, you will get refractive index of denser medium with respect to rarer medium is 1 by sin IC. So this is the relation. You have to keep in mind here 2 is denser and 1 is rarer. So the essential condition for critical angle to get is light must pass from denser medium to rarer medium. Then only you will get this critical angle, and this relation also you can get it, you can use it. Let us solve this question. If a ray of light traveling in air is incident on a glass surface with an angle of incidence 40 degrees, the question is given like this. This is air, this is glass. If a ray of light is incident at an angle of 40 degree, the angle of incidence here is 40 degree. So let us write down angle of incidence I is equal to 40 degree. It deviates through 15 degree. So it was supposed to go this way, but it gets deviated by 15 degree. From air to glass bent towards normal. So this angle of deviation is given as 15 degree. So from here what you know is you can find out the angle of refraction. This angle of refraction R will be, these two are vertically opposite angles. 40 degree, angle I is this one. It will be equal 40 degree minus 15 degree, then you will get the angle of refraction. So here angle of deviation is given 15 degree. So angle of refraction will be I minus the angle of deviation. Angle of incidence is 40 degree minus del, that is 15 degree. It will be equal to 25 degrees. Now let us use Snell's law of refraction, that is sin I by sin R. Sin I by sin R will be refractive index of glass with respect to air, glass with respect to air, and then we call it as reciprocal of sine of the critical angle. Now sin I, it is sine 40 degree, divided by sin R is sine 25 degree, is equal to, here you have 1 by sine IC, the critical angle. Put the values. Sin 40 degree you have 0.6428 divided by sin 25 degree you have 0.4226, that is 1 by sin IC. After decimal you have 4 digits, so remove it. So I'm writing here. So we need critical angle, so I'll make it sin IC, reverse it, then here also we get reversed. 4226 divided by 6428. On dividing these two values, then surely you will get this one, as the value is given sin inverse 0.6574, that is sin IC. So IC is equal to sin inverse of 0.6574. This will be given to you. You just have to look and write down. So like this you can get the value of critical angle. We took it here glass with respect to air because denser with respect to rarer we take. That value is equal to critical angle of the medium of the interface. Now total internal reflection. Total internal reflection we sometimes write it as TIR. Total internal reflection is a phenomena due to which light ray, instead of refracting, it reflects back in its own medium when it tries to travel from denser medium to rarer medium. The two conditions you have to keep in mind. Conditions for total internal reflection. These are the two important conditions. Light must pass from or travel from denser medium to rarer medium. This is the first requirement. The second is that angle of incidence must be greater than the critical angle. These are the two important conditions for total internal reflection to take place. Here we use reflection. Now, to understand this, let me take this interface XY separating two media. Suppose this is rarer and this is denser. You already know about critical angle, so it will be a little bit easy to understand. Suppose this angle of incidence is your critical angle. Then the light ray that will travel from A to B, suppose this point is B, must undergo refraction on the surface of the interface XY that you have chosen, separating the two media, rarer and denser. Here the angle of refraction must be exactly 90 degrees. Then that angle of incidence will be called as critical angle that you have learned in the earlier topic. Now, when I increase the angle of incidence slightly, this time this is the angle of incidence, it is greater than the critical angle. Then light, instead of suffering refraction, it will reflect back in the same medium, that means in the denser medium itself. This phenomena we call it as total internal reflection. This total internal reflection phenomena finds application in technology as well. At the same time, we see that phenomena in nature as well. So let us see now in nature what we can do with this phenomena of total, what we can see with the phenomena of total internal reflection. First of all, let us see TIR in nature. The most interesting phenomena of TIR in nature you can see in the form of mirage. Mirage, when you say, it is an optical illusion and it is of two types. One is inferior and one is superior mirage. This inferior mirage, let us see first of all, it occurs due to extreme heat condition. It occurs in extreme heat conditions. Suppose, say in desert areas where the temperature is very high, desert is full of sand. We know that it is full of sand. This sand has a property of absorbing the infrared radiations of the sun. We call it as heat radiation. So as time passes by, the temperature absorbed or the heat absorbed by the sand becomes more and more, and the temperature of the air at the surface of the sand becomes very, very high. And when the temperature is very high, the moisture content is not there at all, the medium becomes very rarer. It becomes rarer. As you go up on the surface of the atmosphere, the density goes on increasing. That means temperature becomes lesser and lesser, and it becomes denser and denser as you go up. So what happens here is, when you are observing a tree, then this tree will appear to be inverted like this. It will appear to be inverted, and at some point, it's like any tall structure it can be, at some point where total internal reflection takes place, that part the traveler feels that as if water is there, a pond of water is present, like that feeling will be there. How it happens, let us see. Light ray that comes from denser to rarer medium, it bends away from the normal, it goes away from the normal instead of going straight, then thereby increasing the angle of incidence. Here the angle of incidence becomes more than this, like that it goes on increasing. If this angle of incidence becomes greater than the critical angle, then a mirage is formed. Then total internal reflection will take place like this. And when light travels from rarer to denser medium, as you know, it bends towards the normal, so it will go up. It goes up. So if a person is standing somewhere here and observing, he feels that the light has come from here. And according to him, if you extend the light ray, then the top of the object will appear to be it will be appearing below the ground, and you will see the image upside down. So it will appear like this. So he will feel that the tree is upside down, or any tall structure you keep, it will appear upside down. And at this point where total internal reflection took place, that point will appear as if a pond is present, and it will be shivering, quivering, the water type of feeling he will have, and he will feel that some water is present at some distance in front of him. But if he comes nearby and see, then this water will disappear. Now this diagram that you can see here, I have taken very near to each other, but it is not a matter of short distance, it is from very far. From very far if you look, then only this type of phenomena will occur, that is your total internal reflection. In exam purpose, if you draw an exam, you don't have to draw this way, like how I have drawn different layers of the ear. You can draw it in a simple way like this. You take the ground level, take one tall structure, say a tree or a tower, allow the light ray to come like this and bend it this way. Keep the observer here, and then along this line, you can go straight so that you can see the tall image downward. It will be upside down. This way you can draw, and you need to prepare a short note on it. You have to write down how the light ray is bending. It's coming from denser to rarer, so it goes away from the normal, so it will come like this. It will form a U shape. When it undergoes total internal reflection at this point, then it will travel from rarer to denser medium, it will bend towards the normal. So overall structure, it will look like a U shape. The second one, that is your superior mirage. Superior mirage is formed in very cold region. Superior mirage is formed in very cold region, and in that case, the whole object on the ground will appear to be floating on the sky. It will look upside down. That mirage, we call it as superior mirage, and superior mirage is also known as looming. We call it as looming. Now let us see the use of total internal reflection in technology. The first thing you have to know here is the fiber optic, or we call this fiber optics or optical fibers. Optical fibers are transparent piece of glass pipe, in which the inner glass is denser and the outer surface you have to make it rarer. or refractive index inside will be higher and refractive index outside will be rarer. This is denser. Like this it will look. It is a fabricated glass pipe. Now what we do with this is we allow the light ray to pass through this fiber optic, and here the angle of incidence at which you allow the light to pass should be greater than the critical angle. Then instead of refraction, total internal reflection will take place. Then again here after coming and striking, again total internal reflection will take place. Like that, in a zigzag way, the light will travel along the fiber optics. It is not only necessary that you will send light through it, you can even send radio signals as well. Other signals also we can send through fiber optics. One thing you will have to remember that this caddling is done in such a way that the making of the glass is done in such a way that this part, the caddling part, does not absorb any light nor it reflects light. It only allows total internal reflection to take place. So if you use this fiber optics, we know till now that light travels in a straight path in geometrical optics, but if you use this fiber optics, you can allow the light to go in a curved way also. If you keep the glass pipe this way, then light will travel this way, it will travel in a curved way, it will travel and go out. So we can make the light to pass in any form we want to pass it. Now let us see some uses of fiber optics, optical fiber. It is used in sending signals as well as light. For sending signals as well as light. It can be in the form of any electromagnetic wave as well as light also it can send. The second one, it is used in studying the internal organs of our body, like our esophagus, our intestine, our stomach. Those things also we can study with the help of fiber optics. And the third application, you can use it for making decorative lamps. You might have seen in market areas like small spikes of fiber optics they use. When light is allowed to pass through it, different colored lights used to come out. Different colored lights will come out along the fiber optics, and it looks beautiful. It's used for decorative purpose as well. The next thing that you'll have to know is in technology the use of total internal reflection. That is your prism, use of prism or use of total internal reflection in prism. Total internal reflection in prism, it is used for visualizing inverted images as erect ones without changing the size of the image, especially when we use astronomical telescope, microscopes, then we get an inverted image. So if you use a prism, a right angle isosceles prism like this, then what we can do is the inverted images we can make it as an erect one, and then we can study the image. Suppose this is a right angle isosceles prism. Here the angle is 45 degree. Here also the angle is 45 degree. If you keep an inverted image, say this AB is the image in front of this prism, light rays that travels from A as well as from B, they will not deviate as they are coming normally and hitting the surface. Let me mark it as PQ as the surface. So it will just pass straight. Then when it comes and strikes here on the surface, Then as this angle is 45 degree, this angle is 90, so this angle also will be 45 degree. Here if I draw one normal, then you know that normal means 90 degree here, so this will be automatically 45 degree. Now critical angle for glass is 42 degree. Critical angle of glass with refractive index 1.5 is 42 degree. Now this angle is higher than the critical angle of the glass. So here total internal reflection will take place, it will come down. The same way here also, if it goes and strikes at the surface, the same thing will happen. Here also total internal reflection will take place. After coming and striking at this point, if you draw the normal here also it will be exactly 45 degree. Here also it will be exactly 45 degree. Because if you draw this line, then you can calculate it. This is 90, this is 45, so this is 45, and here it must be 90, so this also will be 45 degree. Higher than the critical angle, you can see 42 is the critical angle, so it has to undergo total internal reflection. This one also will undergo total internal reflection. You can get the image erect. This way it will come out. A will come here, B will come here. You can put one dash you can put. AB is the object, A dash B dash is its image. You can look here from A, the ray that is traveling. So this is A dash, and B, the ray is traveling this way. So the point is B dash. So likewise, like this, we can make the inverted images as erect ones in right angle isosceles prism. So here sometimes some numerical counts, let us do and see. They may give the angle different here. Let us see and calculate and find out whether the light will undergo total internal reflection or not, or whether the light will go away out of the prism. We will come to know. Here it comes like this in example questions. A ray PQ incident normally. Here you can see that a ray PQ is incident normally on the face AB, is refracted in the prism. If it comes normally and strikes the surface, you just go straight, that you know already. Material of the prism, the refractive index is 1.5. Refractive index of this prism is 1.5. Think that you don't know it is made up of glass or not, just this value can change, vary from material to material. Compute the path of ray through the prism. Complete the path of ray through the prism. Now what you will have to do is you have to think what angle it is coming and striking. You will draw one normal here. This angle is 90 degree. They have given this as 60, so this one must be 30 because total angle should be equal to 180. Now if this is 30, this is 90. 90 plus 30 is 120. 120 plus how much is 180? Then you come in your mind it is 60 degree. If it is 60 degree, then this angle will be how much? Because this side is 90, this one also is 90. This angle is 30 degree. Like this, you have to calculate the angle of incidence. Here, solution when you do, they ask you to justify as well. So you have to do numerically and show. Angle of incidence I is equal to 30 degree at point. Let us mark at point M, suppose. This is point M. So is this angle greater than the critical angle or it is smaller than the critical angle? That you will have to find out. If this angle 30 degree is greater than the critical angle, then we will reflect. But if this angle of incidence is less than the critical angle, then it will refract. Let us see either way it may go. So what you will do is you will find out the critical angle of you will find out the critical angle here at this point. Critical angle to find out, you have your formula refractive index of glass with respect to air. It is reciprocal of critical angle sin IC, or you can cross multiply. Sin IC is equal to 1 by refractive index of glass with respect to air. Then 1 by critical angle of glass with respect to air. They have given to you the refractive index 1.5 is 1.5. Then this is 10 divided by 15. So it is 2 by 3. So IC will be sin inverse of 2 by 3. Now, this sine inverse of 2 by 3 has to be given to you in the question. Sine inverse of 2 by 3, they will give you the value. By looking at value, you will put it. Therefore, IC is equal to 42 degree. Sine inverse of 2 by 3 is 42 degree. Now, compare it. Is this angle of incidence greater than the critical angle? Then you say no. So light will not undergo total internal reflection. Instead, it will undergo a refraction. It will mark out this side. So here we will write like this. Since angle of incidence is less than the critical angle, the ray will not undergo TIR, total internal reflection. Instead, it will refract on the surface AC. Now, if it refracts on the surface AC, light is traveling from denser to rarer medium, so it will go away from the normal. Let it be MN. So, in which direction the light will pass? Then we will say the ray will pass along MN. The reflected ray will be along MN. Like this, you can do the numericals. Here, please note that these values, they may change. The values will change. Here also, it may come normally. Sometimes it may come with some angle. They may ask question here on this surface or at this surface or at this surface. We never know, so you need to be prepared. But one question if you do, then I think most of you will be able to do. Thank you and have a nice day. Stay tuned with LFI Educates.